Power factor is a measure of how efficiently an electrical device converts electrical power into useful work. It represents the ratio of real power, which does useful work, to apparent power, the total power consumed. The formula for power factor is real power, measured in kilowatts, divided by apparent power, measured in kilovolt amps. Power factor can range from 0 to 1. A power factor of 0 means no real power is being used, only reactive power, which can be inductive or capacitive. A power factor of 1 means all power is being used efficiently, and there is no reactive power. There are different types of power factors. Firstly, lagging, which is a power factor less than 1, indicating a predominance of inductive loads such as motors and inductors. Secondly, leading, which is a power factor greater than 1, indicating a predominance of capacitive loads such as capacitors. Thirdly, unity, which is a power factor equal to 1, indicating no reactive power consumption. A low power factor has several negative consequences. Firstly, increased energy consumption. Reactive power adds to the current flow but does not do any useful work. This requires utilities to generate and distribute more power than necessary. Secondly, increased transmission losses. Reactive current causes additional heating in transmission lines, transformer windings, and other electrical equipment. Thirdly, electrical system stability issues. A low power factor can put additional strain on the electrical system, leading to voltage instability and potential blackouts. Power factor is used in several ways. Firstly, power factor correction. Devices called power factor correctors are used to adjust the power factor by adding either capacitance for lagging power factor or inductance for leading power factor to the circuit. Secondly, utility billing. Utilities may charge customers with low power factors to incentivize the use of energy-efficient devices. Thirdly, electrical system design. Engineers consider power factor when designing electrical systems to ensure efficient power consumption and minimize losses. Power factor is used in a wide range of applications, including industrial motors, lighting systems, power electronics, renewable energy sources, and data centers. Inductive loads, such as motors and transformers, require both real power, measured in kilowatts, to perform work, and reactive power, measured in kilovolt amps, reactive, to establish and maintain magnetic fields. Capacitive loads, such as capacitors, supply reactive power to the system. The presence of reactive power causes the current to lag or lead the voltage, resulting in a power factor less than 1. A power factor of 1 indicates that the current and voltage are in phase, and all the power is being used to perform useful work. Power factor correction involves adding capacitors or inductors to the electrical system to offset the effects of reactive loads. Capacitors are typically used to correct lagging power factors, while inductors are used to correct leading power factors. The goal of power factor correction is to bring the power factor as close to 1 as possible. Power factor is important for several reasons. Firstly, it reduces energy costs. By improving the power factor, businesses can reduce their energy bills and save money. Secondly, it increases system capacity. A higher power factor allows the electrical system to deliver more real power without exceeding its capacity. Thirdly, it improves voltage stability. Power factor correction can help to stabilize the voltage in the electrical system, which can prevent equipment damage and outages. Fourthly, it reduces transmission losses. By reducing the amount of reactive current flowing through the electrical system, power factor correction can reduce transmission losses and improve the efficiency of the system. To understand power factor more deeply, it's helpful to consider the relationship between real power, apparent power, and reactive power. Real power is the power that is actually used to perform work, and it is measured in kilowatts. Apparent power is the total power that is supplied to the electrical system, and it is measured in kilovolt amps. Reactive power is the power that is required to establish and maintain magnetic and electric fields, and it is measured in kilovolt amps reactive. The relationship between these three types of power can be represented by a power triangle. The power triangle is a right triangle, with real power as the adjacent side, reactive power as the opposite side, and apparent power as the hypotenuse. The angle between the real power and apparent power is the power factor angle, and the cosine of this angle is the power factor. The power factor can also be calculated using the following formula: power factor equals real power divided by apparent power. This formula shows that the power factor is a measure of how much of the apparent power is actually being used to perform useful work. A power factor of 1 means that all of the apparent power is being used to perform useful work, while a power factor of 0 means that none of the apparent power is being used to perform useful work. In practice, most electrical systems have a power factor between 0.8 and 0.95. This means that some of the apparent power is being used to establish and maintain magnetic and electric fields, but most of it is being used to perform useful work. There are several factors that can affect the power factor of an electrical system. These factors include the type of loads connected to the system, the amount of reactive power being generated by the system, and the voltage and frequency of the system. Inductive loads, such as motors and transformers, tend to have lagging power factors, while capacitive loads, such as capacitors, tend to have leading power factors. The amount of reactive power being generated by the system can also affect the power factor. If the system is generating a lot of reactive power, the power factor will be lower. The voltage and frequency of the system can also affect the power factor. If the voltage or frequency is not stable, the power factor will be lower. There are several ways to improve the power factor of an electrical system. These methods include adding capacitors to the system, adding inductors to the system, and using power factor correction equipment. Adding capacitors to the system is the most common way to improve the power factor. Capacitors generate reactive power, which can offset the effects of inductive loads and improve the power factor. Adding inductors to the system can also improve the power factor, but this is less common than adding capacitors. Inductors absorb reactive power, which can offset the effects of capacitive loads and improve the power factor. Power factor correction equipment is a type of equipment that is designed to automatically improve the power factor of an electrical system. This equipment typically uses capacitors or inductors to generate or absorb reactive power as needed to maintain a high power factor. Power factor is an important concept in electrical engineering. By understanding power factor and how it is used, you can improve the efficiency of electrical systems, reduce energy costs, and improve the stability of the electrical grid. Power factor correction is often implemented using capacitor banks, synchronous condensers, or static var compensators. Capacitor banks are relatively inexpensive and easy to install, making them a popular choice for many applications. They provide a fixed amount of reactive power compensation, which can be sufficient for systems with relatively stable loads. Synchronous condensers are rotating machines that can provide both leading and lagging reactive power compensation. They are more expensive than capacitor banks but offer greater flexibility and control. Synchronous condensers are often used in large industrial facilities and power plants where precise power factor control is required. Static var compensators, or SVCs, are electronic devices that can provide rapid and continuous reactive power compensation. They use thyristors to switch capacitors and inductors in and out of the circuit, allowing them to respond quickly to changes in load conditions. SVC are often used in transmission systems to improve voltage stability and prevent voltage collapse. The choice of power factor correction method depends on the specific application and the characteristics of the electrical system. Factors to consider include the size of the load, the variability of the load, the cost of the equipment, and the required level of power factor control. In addition to improving the efficiency of electrical systems, power factor correction can also reduce the harmonic distortion in the system. Harmonic distortion is caused by nonlinear loads such as electronic ballasts and variable frequency drives, which draw current in a non-sinusoidal manner. Harmonic currents can cause problems such as overheating of equipment, misoperation of protective devices, and interference with communication systems. Power factor correction equipment can help to filter out harmonic currents and reduce the level of harmonic distortion in the system. When evaluating power factor, it's important to consider the power factor at different points in the electrical system. The power factor at the load is typically the lowest, due to the presence of inductive loads. The power factor at the service entrance is typically higher, due to the effects of power factor correction equipment. The power factor at the utility substation is typically the highest, due to the effects of large-scale power factor correction equipment. Utilities often require customers to maintain a certain power factor, typically 0.9 or higher, to avoid penalties. This is because a low power factor can increase the losses in the utility's transmission and distribution system. Power factor is also an important consideration in the design of renewable energy systems such as solar and wind power systems. These systems often use inverters to convert DC power to AC power, and inverters can generate harmonic currents and reactive power. Power factor correction equipment may be required to maintain a high power factor and meet utility requirements. In summary, power factor is a measure of how efficiently electrical power is used. A low power factor can lead to increased energy costs, reduced system capacity, and voltage instability. Power factor correction can improve the efficiency of electrical systems, reduce energy costs, and improve the stability of the electrical grid. Power factor is a crucial aspect of electrical systems, significantly impacting their efficiency, stability, and overall performance. It is essential for engineers, facility managers, and anyone involved in electrical system design and maintenance to understand power factor and implement appropriate correction techniques to optimize system performance and minimize energy costs. Furthermore, ongoing monitoring and maintenance of power factor correction equipment are necessary to ensure continued effectiveness and prevent potential issues. Regular inspections, testing, and adjustments can help to maintain optimal power factor levels and prevent equipment failures. Power factor analysis can identify areas where power factor correction is needed. This involves measuring the power factor at various points in the electrical system and identifying loads that are contributing to a low power factor. Once these loads have been identified, appropriate power factor correction equipment can be installed to improve the power factor. Power factor correction is a cost-effective way to improve the efficiency of electrical systems. The savings in energy costs can often pay for the cost of the power factor correction equipment in a relatively short period of time. In addition to the direct cost savings, power factor correction can also improve the reliability and stability of the electrical system. This can reduce the risk of equipment failures and outages, which can be costly and disruptive. Power factor plays a crucial role in the efficient and reliable operation of electrical systems. By understanding power factor and implementing appropriate correction techniques, businesses and organizations can save money, improve system performance, and reduce their environmental impact. The principles of power factor also apply to smaller-scale electronics. While the effects may not be as dramatic as in industrial settings, power factor considerations are still relevant in devices like power supplies and LED lighting. Many modern electronic devices incorporate power factor correction circuits to meet regulatory requirements and improve energy efficiency. These circuits typically use active power factor correction techniques, which involve switching transistors and control circuits to shape the input current waveform and improve the power factor. Active power factor correction is more complex than passive power factor correction, which uses capacitors and inductors to correct the power factor, but it offers better performance and can achieve a power factor close to 1. Power factor correction is not only important for reducing energy costs, but also for improving the quality of the electrical grid. A low power factor can cause voltage fluctuations and harmonic distortion, which can affect the performance of other equipment connected to the grid. By maintaining a high power factor, businesses and organizations can help to improve the overall stability and reliability of the electrical grid.